Hi, I'm Sean Moran with ACC GIS, and our topic today is geoanalytics. We'll start our discussion with participatory mapping because these initiatives often combine location-based data and analysis to improve understanding. Participatory mapping, also known as community mapping, combines the tools of modern cartography with participatory methods to record and represent the spatial knowledge of local communities. It is based on the premise that a community's inhabitants know their community and surrounding lands best. Participatory mapping initiatives are often planned around a communal question, in which locals actually provide the source data and local knowledge required to analyze the information and answer the question. The result is a product that represents the knowledge of the entire community. Participatory mapping is a powerful tool that empowers remote and marginalized communities to tackle complex environmental, economic, and social challenges. One of my favorite examples of participatory mapping is the digital Matatu story, a joint effort between MIT, Columbia University, the University of Nairobi, Group Shot Design Consultancy, and the citizens of Nairobi, Kenya. I used to live in the U.S. Virgin Islands and traveled around the islands on an informal mass transit system of vans called jitneys. You'd have to signal them to stop by casually pointing to the roadway. If you waved like a crazy tourist, they'd often just drive right by you. In Nairobi, residents travel via an informal mass transit system of buses called matatus. Like my experience in the Virgin Islands, there was no map or schedule available for the matatus. This 8-minute video tells the digital matatu story and how Nairobi is working to formalize their mass transit system.
It is the buses, the taxis in Durban, the danfos in Lagos, the daladalas in Dar es Salaam, and the matatus in Nairobi that form the very backbone of public transit in African cities. In Nairobi, only about 15% of households own cars. The vast majority relies on matatus to get around the city. Without the matatu system, it's likely that the city would grind to a halt. Improving this system is urgent and critical. Congestion, air pollution, and greenhouse gas emissions linked to climate change are real problems for African cities like Nairobi. Improving the bus systems is a key part of the solution. Yet surprisingly, little open information needed to improve the bus systems exists for passengers, planners, policy makers, and researchers.
Like a capital in Nairobi, you're using matatus, you're using bus. How can you get information which bus is using which route, where is it heading to, the kind of destination, the path which it follows, the kind of stop which we have, and how frequently can you be able to get a bus?
These bus systems often seem to be chaotic and complex, and data on them elusive, but technology is transforming the way we relate to transit. Digital matatus is a key player in the movement to make transportation in the developing world more efficient and open. A collaborative project of the University of Nairobi, Columbia University's Center for Sustainable Urban Development, MIT's Civic Data Design Lab, and Group Shot have been collecting and standardizing transit data for Nairobi's matatu systems, the city's decentralized city bus system, making it open and available to the public for the first time.
So the Digital Matatu project is started off as a research project around looking at how do people in the informal settlements move about. We've been able to put together data that maps the maps Nairobi's matatu or public transit system accurately. The data is in digital form and is available for anybody who would like to use it. It's open. The data comprises of the actual tracks that are used by matatus, inbound and outbound. We also have information about where the stops are. We've mapped out close to almost 3,000 bus stops, or what we normally in Kenya refer to as stages, bus stages. That also includes terminals and so on. We've also, within the project, the other data that we're able to put together was tentative schedules based on frequency of the dispatcher from the main terminus on the data side. We then use this data to develop a map, a stylized map of the Nairobi transit system. And so we also have the Nairobi matatu routes in a stylized format, and this can be downloaded and printed on a map. We already have a few maps like the one behind me.
Armed with cell phones, University of Nairobi's students rode and followed every route, all 136 of them collecting data as they went. Matatu drivers, university students and other citizens helped give critical feedback throughout the development of the data and map, a real example of a bottom-up approach. Digital Matatus has literally helped put Africa's systems on the map. This work is now spreading to Kampala, Maputo, Lusaka and Accra. Since a launch in collaboration with Nairobi County and the Kenya Alliance of Residents Association in January 2014, the data and map have been used to improve the experience of matatu riders, with some developers using this project as a launchpad for crowdsourcing data on accidents and crime, while others have developed a mobile payment system that calculates the correct payment for riders' trip to combat price fluctuations.
As for example, depending on where I'm located, I can actually ask the system to tell me what's the nearest bus stop. And then basically what it does is that it checks the GTFS data, the data that we have for Nairobi, looks at my position and then suggests when the nearest stage is.
Nairobi is planning the bus rapid transit corridor number 1, which is coming from Kangemi down to the airport, passing through the CBD. So we can see that the original digital matatu maps that were produced by the university have been the first piece in the whole circle of introducing public transport solutions for Nairobi.
When you're sending out people to collect data, you need to first of all find the most optimal kind of route for them to take. You must find the most optimal way for them to collect this data. So we actually use the digital matatu map to be able to station people in different places, because then we know, depending on where you live, this is the kind of matatu one that you're going to take. This is what will be the shortest distance. This is what will give us the most effective results.
So personally, I'm benefiting a lot from the digital matatu map, which you can either print out as a map or you can also download the app. So for me, being a foreigner in Kenya, it helps me a lot to find my way around in Nairobi and in the outskirts of Nairobi, since I can see on the map exactly which matatu number is taking which route. So instead of asking around in town, asking the conductors, asking the drivers, I can actually just use the app or look at my printout and figure it out myself.
Digital Matatu continues to work in Nairobi to create a sustainable, long-term means of producing high-quality open data for public transit to spur innovation, transparency, and service improvements. Better transit by leveraging technology, data, and engaged citizens will be critical to less congested, connected, clean, and low-carbon cities in the continent.
Now, what I really love about this story is how GIS academics and volunteers employed readily accessible technology like mobile phones and apps to collect and analyze data to improve a community service. If you're interested in learning more about participatory mapping, check out the links on this slide, including a video from ESRI's education manager, Dr. Joseph Kursky, who teaches you how to use cloud-based applications like Google Forms, Google Sheets, and ArcGIS Online to support participatory mapping projects. Our objective is to use geoanalytic models and methods to analyze geospatial data. By the end of this topic, you should be able to define geoanalytics, describe different geospatial models used in geoanalytics, describe different geoanalytic methods, name 3 GIS software packages used for geoanalytics, and perform geospatial analysis using GIS. Geoanalytics combines location-based data and analysis to improve understanding. This term is often used interchangeably with geospatial analysis and spatial analysis, and they all describe our efforts to improve our understanding of how the world looks and how the world works. Now, geoanalytics can be used to improve our understanding of how the world looks by modeling geographic entities as vector, raster, and triangulated data. We can also measure those entities by calculating the geometric properties or statistics of the data. We can classify those entities by grouping geospatial data according to a common characteristic. And we can query those entities by searching and retrieving records in geographic features or cells. Up to this point in the ACCGIS program, we've really been focused on understanding how the world looks. But we also want to understand how the world works, or what are those spatial relationships between the geographic entities. And we can explore those spatial relationships by performing proximity analysis to locate nearby features or cells, overlay analysis to intersect overlapping features or cells, connectivity analysis to explore connected features or cells, and custom analysis to perform customized spatial analysis. Let's take a look at a railway network example and how we can use geoanalytics to combine location-based data analysis to improve understanding. When we look at how the world works or those geographic entities, a railway is typically modeled in a GIS as a vector line, for example, with a freight attribute. We might want to measure the railway or calculate, for example, the total length of a railroad, or classify railroads by freight volume. We also might want to query this geographic entity to locate the railroad segment with the most freight. But again, we can also use geoanalytics to understand how the railway network works, or the relationship between the railroads in a railway network or the railway network with other geographic entities. For example, performing a proximity analysis to locate schools within 500 feet of a railroad, or performing an overlay analysis to intersect railroads with roadways to identify crossings. We can also look at the connectivity by quantifying the impact a new railroad might have on travel time. Or even a custom analysis, like, for example, predicting top speed in different weather conditions to minimize the chances of derailment. Now, this example isn't out of the blue. I actually was able to tour BNSF Railway in Fort Worth and see their command center. And all of those geoanalytics that I described in the previous slide, they are doing in this room. It was really amazing. It's like being at the command center for NASA with all of the information for their entire system, both on the computer screens and the workstations, but also projected on the back of the wall there. And they do all of those types of analysis, including the custom analysis, where they're looking at real-time weather reports, temperature, humidity, and wind speed to predict the maximum speed that they can run their trains while minimizing the chance of derailment. So this is just one industry. Imagine all of the different ways we can use geoanalytics and GIS to better understand how our world looks and works.